Hi everyone, I just want to go through another vector application problem here. This is another one of those little tricky ones that I think requires some explanation and you being able to rewind a few of the things here. I haven't got the problem on the page here, but this is the problem, so I'm going to tell you what it is. I think it's pretty easy to understand. We have got a bee situated at the point P, and we want the bee to go from where it is at P to Q, which is a flower. That's where the bee wants to go to. There is, however, complicating things, a breeze blowing, and this is the vector that the breeze is blowing at. Okay, we've got the idea there. Alright, and the maximum speed that the bee can go at is 10 meters per second. What we want to find out, of course, is the velocity with which the bee has to fly to reach the flower in minimum time. So if the bee just sets off on a direct course from P to Q, it's not going to make it because the breeze is going to blow it off course. So there's a bit of vector stuff going on here. This is a cool question, so let me take you through it. And I've got two different ways of doing this question, and I want you to appreciate both ways of doing it, and it involves using your calculator as well. Okay, so firstly, the direction from P to Q is Q minus P, of course, and that is, I've done the calculation, 11, negative 8, 10. That's the direct line from P to Q. Okay, so if the bee's velocity is v, what I'm saying here is that the minimum time is going to happen if the resultant velocity, that is, where the bee heads, and then you add on the wind, if you add those two together, you're going to get a vector that's parallel to P to Q. I hope that makes sense. Okay, so in other words, written algebraically, it looks like this. The bee's velocity, which we're calling v, and that's going to be in component form with an x, y, and z component, plus the wind here is going to be some scalar, some multiple of the vector in the direction of P to Q right here. Okay, so let's do a little bit of algebra on that. If I basically subtract the wind from both sides, I get this expression right here. Okay, which is an expression for the velocity of the bee in terms of lambda. Now lambda, remember, was just some scalar that's going to help us to get in the direction from P to Q. Right, so what do we know? We know that the velocity at maximum is 10 meters per second. So then what I'm going to do is I'm just going to say the velocity, the length, if you like, of this vector v is going to be equal to 10. So what does that look like? That looks like that at the bottom there. So you square each of the components and you square root it, sorry, and you should get 10. So that first step there, I've squared both sides. Now this is where you get your CAS calculator out and you solve for lambda, and your calculator will tell you that lambda is equal to 0.55267. Alright, so a little bit over halfway along from P to Q. So you put that value of lambda into this expression here, and here, and here, and that will give you the velocity for B. So when I do that, I get 7.1, negative 5.4, 4.5. That's the direction that the bee needs to head to get there. Here's another way of doing it. Let me go through this method closely. Okay, speed is distance over time, so distance is speed times time. The distance here is P to Q. That's where we want to get to. What's our speed? Well, our speed is the speed of the bee plus the wind. Okay, that's the total speed of the bee. The wind's going to be kind of pushing the bee along there in that direction. And once again, this is hard to imagine in 3 dimensions, isn't it? Really hard to draw. I wish I could draw a diagram here. Really hard to draw. So that's the velocity of the bee in that brackets there times time. Okay, and again, rearranging. I've written the expression in here for P to Q, and I've divided, which is 11, 8, negative 10. I've divided both sides by t, and then from this step to this step here, I've just once again subtracted off negative 1, 1, 1, and I end up with this expression right here, which is an expression for the velocity of the bee in terms of t this time. Again, we know that the velocity, or the length of this vector here, is at maximum 10, and we're going to want the bee to go maximum velocity to get there as soon as possible. So again, we use our calculator, and put that big long expression in. The calculator solves that and gives me two answers. One of the answers we're going to ignore for now. That's the negative answer there. But we're going to take the positive answer, 1.8094 seconds. So that's how long it takes. But the question said, what's the velocity? So I then need to substitute in t into here, here, and here to get the velocity. And lo and behold, you get the same answer that I got in the first part. Cool? Next question, what's the minimum flight time? Well, this is where it's handy to use the second method, because I can see the minimum flight time would be 1.8094 seconds, or 1.81 seconds if you like, for the bee to get from where he was to the flower. Okay, last question here is, what is the velocity that the bee needs to fly at to get from the flower back to where he originally was in the minimum time? Okay, so let's deal with that. How do we get back to where we were in the minimum amount of time without going through the whole process again? The trick is recognizing that this other solution to t is the value that you need to get back in the minimum time. So even though in this context negative 1.6 seconds doesn't make sense, that's the value of t that you use to substitute into this expression here again, this one right here again, and that will give you the velocity to get back in the minimum amount of time. So I've done that, and I get this vector right here, which is the answer to that one. So if the question then said, I could make up part D of this question, what's the total flight time, assuming the bee just landed at the flower and came straight away back, then the total flight time would, you'd just add these two together. It would be 1.8094 plus 1.6238. That would be the total flight time from getting from there and back again.